Hello everyone, welcome to the video explanation for Brian Passwater's topic 1-3 notes, example 4. Now example 4 does the same sort of thing as example 3, except instead of asking whether the function could be linear, quadratic, or neither, instead we are looking at whether or not the function could be concave up, concave down, or neither over the domain provided in the problem. So again, what we're looking for here is how does the rate of change over those intervals behave? If it is concave up, then the AROC will be increasing. If it is concave down, the AROC will be decreasing. And if it is neither, that implies that it is linear, which means the AROC is constant. So really all we're looking at is the average rate of change increasing, decreasing, or neither? So on part A, to look at the AROCs, we look at the change in x. Well, the change in x is constant. It is always increasing by 0.1. So we have equal length input value intervals. Now for k of x, we're looking to see, well, what does it do? Well, here we have a -3, then a -2, then a -1, which means the AROC would be -3 over 0.1, which is -30. Then we would have -2 over 0.1, which would be -20, and then -1 over 0.1, which would be -10. That AROC is not the same every time, so it is not constant, which means it is either concave up or concave down. And in this case, because that AROC is becoming less negative, the AROCs are increasing. So we would say k of x could be concave up, because the AROCs are increasing. If the AROCs are increasing, the graph is concave up. Now we have the exact same x pattern on all of these tables. So on part B, we are going to look at, okay, well, all the x's are still increasing by 0.1. The m of x values are increasing as well by 3 each time. Now what does that mean? That means our AROC is 3 over 0.1, or 30, for all 3 of those intervals. If your AROC is constant, we could say that m of x could be neither concave up or concave down, because the AROC is constant. Now, we don't know what happens between those x values, so it is possible that it could be the other. Okay? All right, then finally we have the third example. Again, all of our x values are increasing by 0.1 each time. And our p of x values, they're increasing as well. However, they're not increasing by the same amount each time. As a result, the AROCs are not constant. We have 6 divided by 0.1, which is 60. We have 4 divided by 0.1, which is 40. And we have 2 divided by 0.1, which is 20. So the AROCs are not constant, which means it is either concave up or concave down. And in this case, the AROCs are decreasing, which means that p of x could be concave down. Because those AROCs are decreasing. So that's sort of a quick look at the discrete side of functions and how we tell whether they're concave up, concave down, based on the average rate of change. And again, you need to consider the average rate of change, not the function itself. So make sure you're reading these problems carefully and considering what you know about rate of change, concavity, and just the function values themselves.